Hi, in this module we'll discuss how by placing a subject in an MR scanner, we can obtain a signal which can subsequently be used to create an image. In order to understand this process better, we need a little background on MR physics. This is a course in itself, and by necessity we're going to have to discuss this topic in a very simplified manner. For those of you interested in exploring this area more, I'll put some references in the discussion section. But before we get to MR physics, let's discuss the scanner in which we use to get these images. An MR scanner consists of an electromagnet with a very strong magnetic field. Typically they're between 1.5 and 7 Tesla. Now, what does that mean? Well, consider that the Earth's magnetic field is 0.00005 Tesla. That means that a 3 Tesla magnet is 60,000 times stronger than the Earth's magnetic field. So these magnets are quite strong, and one needs to be careful with bringing metallic objects in close to them, or for example a credit card, which would be erased if you went into the scanner. MRI is an extremely versatile imaging modality that can be used to study both brain structure and brain function. So both structural MRI scans and functional MRI scans are both acquired using the same scanner. Now, different types of brain images can be generated to emphasize contrast, which is related to different tissue characteristics. We'll discuss that more as we move along. All magnetic resonance imaging techniques really rely on a core set of physical principles. And to really understand, we have to begin by studying a single atomic nuclei and illustrate its impact on the generated MR signal. So, in MR in particular, we focus on hydrogen atoms consisting of a single proton. So these are also called hydrogen 1 atoms. If we look at a hydrogen 1 atom, these protons can be viewed as positively charged spheres which are always spinning around like a top. Now they give rise to a net magnetic moment along the axis of the spin, so along the arrow in the figure here. And since they're spinning around, we can alternatively represent the proton in the following manner, where the cylindrical-like shape shows the trajectory of the vector across time. So while the proton spins around like a top, the direction of the magnetization moves around in its cylindrical fashion. Now, we're not able to measure the magnetization of a single proton using MR. Instead, what we measure is the net magnetization of all the nuclei within the entire volume. So in our case, all the nuclei within the slice of the brain that we're interested in looking at. This net magnetization can be viewed as a vector which has two components. The first is a longitudinal component which is parallel to the magnetic field, and the second is a transverse component which is perpendicular to the field. So if we make a little cartoon image of this, here we have a vector, which is the green arrow here, and which is written out in three-dimensional space. And so we have the x-axis, the y-axis, and the z-axis. So if we look at this, we can see that this vector has both a longitudinal component and a transverse component, measured as follows. Now going back to our proton, in the absence of an external magnetic field, the nuclear magnetic moments are randomly oriented vis-a-vis each other. So that means that if one proton is pointing in one direction, there's going to be another proton pointing in the opposite direction that cancels it out. So what we have here is no net magnetization, so the vector would be 0 in this case. So when placed in a strong magnetic field, this causes the nuclei to align with it, and this creates a net longitudinal magnetization in the direction of the field. So if we look at the coordinate system at the bottom here, we see that we have a longitudinal component to this vector. Now, while they're aligned, the nuclei process about the field with an angular frequency, which is determined by what's something called the Larmor frequency. However, they process at a random phase vis-a-vis each other. What we do then is we use a radio frequency pulse to align the phase. And so now they're all rotating in phase with one another and tip over the nuclei. This causes the longitudinal magnetization to decrease and establishes a new transversal magnetization. So, as you see now, the vector is pointing in the transversal direction, and then there's no longitudinal magnetization left. After the RF pulse is removed, the system will seek to return to its equilibrium. So the transverse magnetization will start to disappear in a process which we call transversal relaxation, and the longitudinal magnetization will grow back in a process that we refer to as longitudinal relaxation. And during this process, a signal is going to be created that can be measured using a receiver coil. The analogy I like to make here is with a compass needle. So suppose that we have a compass which is pointing north. What we can do is we can open up the casing of the compass and with our finger, we can force the compass needle to point east instead. Now, once we remove our finger, what's going to happen? Well, the compass needle wants to point north, so it's going to return to its original position. So longitudinal relaxation, this is the restoration of net magnetization along the longitudinal direction, so in the z direction, as the spins return to their parallel state. Now, typically, longitudinal relaxation, this is described by exponential growth, which is described by a time constant t1. We'll discuss that more in a second. Transverse relaxation is the loss of net magnetization in the transverse plane, so in the xy plane, due to loss of phase coherence. And this is an exponential decay, which is described by a time constant t2. Here is an illustration of longitudinal relaxation. So basically what happens is we've tipped over the nuclei so they're pointing in the transverse direction. But once we remove the RF pulse, the magnetization grows in the z direction as the nuclei return to their original line position. And this curve describes the manner in which it returns to its original line position, and we get back to our original net magnetization, which is m0. This process is described by a time constant t1, and that's defined to be the time it takes for the net magnetization in the z direction to return to 63% of its original value. The interesting thing is that different tissue types have different T1 values. So, for example, white matter has a T1 value of 600 milliseconds. Gray matter has a T1 value of 1 second, while CSF has a T1 value of 3 seconds. So this is an interesting thing, and so this is what we're going to be able to use later on in order to be able to tell white matter and gray matter and CSF apart from one another, and this is what we use in order to create images. Transverse relaxation is the decay of magnetization due to interaction between nuclei. And so remember, when we began, all the nuclei were out of phase with each other, but once we applied the RF pulse, first the nuclei were put into phase and then they were tipped over. At the moment the RF pulse is removed, all the nuclei are in phase with each other, but once it's removed, they'll seek to go out of phase with each other, and that will kind of disturb some of the coherence in the xy plane. And so after a while, all the nuclei will be pointing in different directions, and the xy signal will thus disappear. And this is described by the following curve. And here we start out with mxy, which is the signal in the transverse plane, and then it decays down to 0 as we return to equilibrium. Now T2 is the time constant that describes this process, and this is the time point when we reach 37% of the original mxy value. By altering how often we excite the nuclei, and this is described by a term called TR, and how soon after excitation we begin data collection, and this is described by a term TE, we can really control which characteristic of the brain or the sample which is emphasized. Roughly, the measured signal is approximately equal to m0 times 1 minus e to the minus tr divided by t1 times e to the minus te divided by t2, where again t1 and t2 are tissue properties. So we're going to have a term m0, which is the net magnetization in equilibrium. We're going to have a term that depends on T1 and TR, and we're going to have a term that depends on TE and T2. Now we're allowed to control TR and TE, and by controlling TR and TE, we can choose to emphasize whether this is the m0 value is going to be weighed by T1 or by T2. Now the ultimate goal of fMRI is to construct an image, or a matrix of numbers that correspond to spatial locations. And so the image is going to depict the spatial distribution of some property of the nuclei within the sample. Now this could be the density of the nuclei, so how many hydrogen atoms are within a certain part of the brain, or the relaxation time of the tissue in which they reside. Here's an example of how we can get these types of images, and this is the type of image contrast that we're interested in. So for example, if we choose a long TR and a long TE, what happens in this case is the long TR is going to cause this term, the E minus TR divided by T1, to be close to 0. And so now the signal is going to be m naught times the exponential term which depends on TE and T2. So now what we're going to get is we're going to get what's called a T2 weighted image. If we instead choose the TR to be long and the TE to be short, well then the first exponential is going to be 0 and the second one is going to be close to 1. So hence the signal will be roughly proportional to m naught. And so that's the net magnetization, and that's in turn proportional to the number of protons that we're scanning. And so in that case we'll get what's called a proton density image. If we take a short TR and a short TE, what happens in that case is now the second exponential is close to 1, and we're going to get a signal that's m naught times what's in the first parentheses there, 1 minus e to the minus tr over t1. So this is going to be an image that's the signal is going to be weighted by the t1 value. Finally, if we take a short tr and a long te, we just get garbage. So this is not a useful image. So what I want to illustrate with this image is by choosing different values of tr and te, we can get images that emphasize whether or not the proton density within a sample, the T1 or T2 values, which are tissue dependent. And so by doing this, we can get images that look quite different, that emphasize different things about the brain. And we'll see this in these 3 images here. T2 star is the combined effect of T2 and the local inhomogeneities in the magnetic field. The interesting thing is that sometimes there are local inhomogeneities in the field that cause the nuclei to dephase quicker than they would in the absence of them. So this changes the value of T2 somewhat, and we get what's called T2 star. Now the scanner can be programmed to eliminate these effects, or alternatively, the scanner can be programmed to emphasize these. And the later type of procedure is actually what forms the basis of what's called bold fMRI. So in sum, images can be produced that are sensitive primarily to T1, T2, or T2 star. And because T1 and T2 vary with tissue type, we can use that to represent boundaries between things like CSF, gray, and white matter. And because T2 star is sensitive to flow and oxygenation, we're going to be able to use that to image brain function. We'll see that in subsequent modules. All right, that's the end of this module. And so here we've given kind of a layman's overview of MR physics. In the next module, we'll talk about how can we use this signal in order to start creating images. All right, I'll see you then.